Happy day and welcome everybody. Today's lesson is on calorimetry. Now, what we're seeing here is to the left, we actually have a simple calorimeter and it's pretty basic. It's styrofoam, so some type of insulation. We've got a thermometer, we've got something to stir with, and then you put your reactants inside of there. So it's very simple. Then there's what is called the bomb calorimeter. And the bomb calorimeter is not like a bomb going off, but this is typically used for reactions that where something may be burning inside. And so we need a little bit more. Otherwise, if we're using a simple calorimeter, it might just, basically set it on fire, or it'll start to melt or something like that. And then we're unable to get our actual energy changes from that. So let's get right to it. So this really, I want to tell you, is all about experimenting to find delta H. So anytime they say, how can you find the energy change experimentally? Calorimetry is what is going to do it for us. So we use this equipment to be able to figure out how much energy is being released or how much energy is being absorbed. The other thing that it can do for us is if we have different unknown substances and we have specific heat values for those, we can actually use the calorimeter to be able to tell us what the substance is. So that's kind of another use of the calorimeter. And there are different units, and so we'll talk a little bit about that, but it's really just about solving problems together. So the more problems that you do, the better off you're going to be, where you can get any type of calorimetry problem and be able to solve it. So it says if it's not a substance that's going through a phase change, it's a rather simple algebraic manipulation of delta H equals MC delta T. You just have to make sure that all of your variables are for the same substance. So what I mean by that is if your mass is of water, then make sure that your specific heat is of water and your temperature change is of water. But if your mass is of some unknown metal, then your specific heat as well as your delta T need to also be for that particular substance. Now, when you talk about energy, this is really important. We talk about energy. If I put something in the water and I see, for example, that the water's temperature rises, well, what that means is when I drop that in, that one substance must have released its energy to the water. So the water's absorbing that energy. Here's the important part. The amount of energy is the same. So based on what we've been talking about the first law of thermodynamics, that the energy of the universe is constant, that the energy in must be equal to the energy out. So if something is releasing a certain amount of energy into the water must be absorbing that, and that's why if we had a thermometer stuck into the water, we could see, without even seeing the substance, we could see that the temperature of the water rises. So that's kind of how we end up using calorimetry a lot of times, is using water kind of as our base for being able to see what's happening to a different reaction. Okay, so this is a simple equation, but I wanted to make sure that you could see this here, how things may not include water. For example, here it says, one mass of lead will release 259 joules of energy when heated from 50 degrees Celsius to 65.5 degrees Celsius. And then they're also giving us the specific heat of lead. Okay, so we're looking for grams in this situation. So I wanted to give you a little bit of a different problem where, what if we're not solving for joules or kilojoules or calories or kilocalories? What if we're not solving for specific heat? How does the equation work? Well, it's algebra. It works out exactly the same way. So I know the equation is delta H is equal to MC delta T. And I know in this situation, I'm solving for M. Again, just like I said before, if I did say something about water, I do not want to use water in this equation. If I'm using water, I have to use water for everything. Okay? So you could, and sometimes what they'll do is they'll ask you how much energy was released if they drop the lead in the water, and they give you the mass of the water, and they tell you the temperature change of the water, and you already know the specific heat of the water, well, you know everything in MCAT. So that would just be check, 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 calculate M times C times delta T. Again, all of those need to be for water. That gives you the delta H of the water. But since we said if you know what the water changed by, then it must be opposite. So if one thing absorbed energy, the other thing must have released energy, then you know the exact amount of energy is just a difference in sign. That's it. Okay, so in this case here, it tells me that it's 259 joules of energy. I don't know my M, that's what I'm looking for. They tell me the specific heat of the lead is the 0.128 joules per gram degree Celsius. Always double check that my units match here because otherwise it won't cancel out when you go to the algebra. And then my temperature change is 15.5 degrees Celsius since it goes from 50 to 65.5. Now, my answer ends up being, if I divide 259 divided by the 0.128 divided by the 15.5, I get that my mass is equal to 130 sig figs. It's 130.5. So 3 sig figs would make it 131. And what are my units? Well, it's mass, so it's grams. Then people end up asking me, what about the sign? No sign. No sign. The only thing that will get a sign is delta H. Okay, so it doesn't make sense to give mass a sign. You can't say negative 100. So make sure it makes sense when you go to solve these problems, okay? One of the major uses of calorimetry is to measure the specific heats of metals and various metallic alloys. So similar to what I was just telling you, chemists use specific heats in their study of the structure and attractive forces in materials. So this can be very helpful if you are maybe an engineer or you're an architect and you're trying to figure out, okay, well, I want to build something in Arizona versus wanting to build something here in the US. The meaning of specific heat, if you look at the number, now, water's number is 4.184. If we actually looked at numbers for some of the other substances, for example, we're looking at the lead being at about a 0.128. You can see in this problem down here, they're talking about gold, and gold is at a 0.0129. So these numbers are way less than 4. Water tends to have one of the highest specific heat values. What does it mean? Well, basically what it is the higher the number is, the more resistant it is to change, the more energy it requires in order to get that to change its temperature. So we know that when we define heat capacity or specific heat, it's the amount of energy required to raise 1 gram by 1 degree Celsius, to change 1 gram of that substance by 1 degree Celsius. So the bigger that number is, the more energy it requires in order to change that. So that's another important thing is when we look at these numbers, what do these numbers mean? Okay. So specific heat, well, again, the symbol that we're typically going to use is either an S or we can use C for heat capacity, useful for engineers. The use of calorimetry is based upon the law of conservation of energy. Energy is neither created nor destroyed, so it's simply transferred. Okay, so we just end up transferring it. But it can be transformed from one form to another. In this application, this is a really, really common problem. So we've got a hot metal, and it's being added to cold water in a calorimeter. The cold water contains the heat lost by the hot metal as they come to the same final temperature. If you measure the temperature changes, you can actually calculate the heat gained by the water and thus the heat lost by the metal. So what we see is you can either do this as MCAT equals MCAT, or what I've seen people do is they figure out the MCAT for the water, for example, because they know the mass of the water, they know the specific heat of the water, they know the delta T, the temperature change of the water, so they calculate their delta H. And then what they do is they say, well, the energy change must be the same for the metal. So now you know the delta H of the metal. So instead, they'll actually do 2 separate equations of delta H equals MCAT. One for the water, where they figure out what the delta H is, and then the second one, if you know the mass of the substance, and you know what the temperature change was of the substance, then, and you know it's delta H because it's the same as the water's, then you can calculate its specific heat and be able to figure out what your unknown is. So let's take a look at this next problem here. We've got a 28-gram coin of gold, and it's heated to 500 degrees Celsius, and a styrofoam cup is prepared, and it's got 250 grams of water in it at room temperature, 24 degrees Celsius. Okay, now this is important. I want you to make sure that you can picture it. If you can't picture it, it's really hard to solve this problem, okay? So I want you to picture that we've got a hot plate or maybe even an oven or something like that where we've actually heated up this gold, this 28 grams of gold, and we've heated it up to 500 degrees Celsius. Okay, so this gold is really hot. Don't want to touch it. It's really hot, all right? We have the styrofoam cup, and we've got 25 grams or 250 grams, about 250 milliliters of water then, right? And it's at room temperature. It's at 24 degrees Celsius. You're going to drop the hot gold into the water. Well, when you drop the hot gold into the water, what's going to happen? The water's temperature is obviously going to go up. But here's kind of the crazy thing, okay? It's not going to go up as much as you think it would go up. It is going to come to equilibrium. Both of them are going to reach the same temperature, okay? And this is probably one of the hardest types of MCAT equals MCAT problems you can have, but I wanted to make sure that if I was going to do one example for AP, I would make it a more challenging problem, okay? So I'm going to show you how we can solve this more quickly than actually using this long algebra way of solving it, which is typically what people want to do. Okay, so here we go. Now, again, I could do this in two ways. I know I need two MCAT problems. Why? If the solutions are dissolving into each other, you have one solution, you need one MCAT, okay? But in this situation here, I have two substances. I have water and I have the gold. And when I mix the two together, they're not actually going to create one solution. I can, at the end, pull out the gold and take it and go use it somewhere else. So this isn't a chemical reaction that's happening. If it's a chemical reaction that's happening, then you only can use one MCAT. But in this situation, I can use two, okay? So the way that I usually like to set this up is I'm going to put the gold on one side, and I'm going to put the water on the other side, and I'm simply going to use MCAT equals MCAT. And again, the idea is amount of energy lost must equal the energy gained, okay? So what do I know? Well, I know the mass of my gold is 28.0 grams. And I don't know the specific heat. I know the specific heat, actually, of it, and I was about to say for water, we know it, it's just not written in the problem, so I just wanted to make sure you were aware of that. So I've got 0.0129, and they're using joules per gram degree Celsius. Okay, so now here's the tricky part. Okay? So for the gold, I know that it's starting at 500 degrees Celsius, and I don't know what the final temperature is. That's what I'm looking for. I'm looking for the final temperature, okay? So sometimes they'll just say, what's the final temperature of the water? Well, the final temperature of the water must be the final temperature of the gold. So it's both of them, really, okay? Here's the thing. Water's not going to change that much. Water's not going to change that much. So it won't even be significant. And so this is where we're going to save a lot of time. Here is this understanding. So what I'm actually going to do is I'm going to simply say that my starting is at 500 degrees Celsius for the gold, and I'm going to say that it's ending around 24 degrees Celsius. It's not exact, but it's around 24 degrees Celsius. So I'm going to say this number that's going to go in here is going to be my 500 degrees Celsius, and it's going to drop down to about 24 degrees Celsius. And when I subtract that, I get 476 degrees Celsius, okay? Now, here's the thing again. Because I'm at 500, even if this were, I don't know, 24.2 degrees Celsius that water changed by, something like that, significantly, I'm still going to say it's 476, okay? So let's check to see what happens here. Now, the mass of the water, they tell me that I had 250 grams of water, so let's plug that in, 250 grams of water. Remember, everything on the left has to be for the gold, everything on the right has to be for the water in this situation. So now, the specific heat of water, we said that we could use either 4.184 or 0.004184. Because this left side is in joules, I want this right side in joules as well, joules per gram degree Celsius. And now my temperature changed. Okay, this is the best part of this. What you could do is you could say, well, I know that water is starting at 24, but then I don't know the end. You could do that. But I'm going to tell you there's a lot more math that's involved because then you're going to need to distribute and there's a lot more algebra. I guarantee if you try this, significantly your answer will be just about the same, and this is what AP wants you to do. They don't care about checking to see what your incredible math skills are like. This is not what this class is. This class isn't about your incredible math skills. This class is about understanding how to solve the chemistry problems and then making sure that you actually get it, okay? That's what this class is about. So we're going to minimize this now. We're going to change this up. I'm just going to call it delta T of the water. Okay? I'm going to call it delta T of the water. And by the way, what some people will do is they will actually label like MC delta T. So if it's water, they'll say M water, C water, delta T water, just so that they remember these are all for the water. These other ones are all for my metal or for my gold or whatever it is. Okay? All right, so now I'm just going to do this simple calculation here. Okay, and so I multiplied 28 by 0.0129 by 476. I divided by 250 and divided by 4.184. Remember, you have to divide. And what I'm getting for my temperature change of the water is, so the answer I get is 0.1643, 3 sig figs, 0.164. Okay, but this isn't really the answer because it wants to know what the final temperature is of the system. So I know that the original temperature of the water was 24 degrees Celsius. So all I need to do is do my 24 degrees Celsius, add this 0.164. Okay, now, based on our sig figs, the greatest place, I can't go any further than my ones place in reality, okay? Usually what they would do in a problem like this is they would say that room temperature is 24.00 or something like that, okay? And so if we imagine that, if it were 24.00, then we would say that our final answer is 24.16 degrees Celsius. Again, what I want you to notice here is that the temperature did not change very much. Now, here's the question. What if I wanted to do it the long way, algebraically the long way, okay? Well, what you would end up needing to do is, because we know that the temperature started off at, for the metal, it started off at 500 degrees Celsius, then what I would do is I would actually call this 500 minus X. But for the water, because it's the opposite as far as which one's losing and which one's gaining heat, we know that the metal is losing heat and this one's actually gaining heat. This side, I would do as X minus 24 degrees Celsius. Okay, and then what I would do is do all of my algebra out to check to see what X is equal to. It's a lot of algebra. Again, we don't want to do that. Our final answer is what it is. I guarantee if you do that, you're going to get something really, really, really close, at least significantly, to that final answer. Okay. Then we've got a problem where what happens if we end up mixing two things? So just like I had said earlier, what happens if we mix two things into a calorimeter together? So in this example, we have a 0.05 liter sample of a 0.2 molar hydrochloric acid, and it's being added to ammonia, which is a weak base. And so it says that the temperature increase is 1.09 Kelvin. They want to know what the delta H is in kilojoules per mole. Okay, so I'm going to tell you that when you use MCAT, you don't get per mole. When you calculate delta H is in joules, kilojoules, calories, or kilocalories, not per mole and not per gram, okay? It is for the reaction as they told you that the reaction proceeded. If you want it per mole, you have to make sure that you've switched grams to moles for something, or maybe they tell you how many moles it is, okay? So that's really important. Before we also solve this problem, it says the heat released from the reaction is the heat absorbed by the calorimeter and its contents. We've already talked about this. Since the temperature increases, the reaction must be exothermic. It must have released energy, so it's exothermic. So heat was a product. Remember, if it's exothermic, it's a product. So the sign of the product must be a negative delta H. Again, we're only applying a sign to delta H, okay? So let's try this one out. Now, before we do this, I know because they're being mixed together and neutralized together, I only want one MCAT. So people will make the mistake of doing two MCATs in a situation like this, and then they get confused, okay? So this is delta H equals MC delta T. Here's the other thing. They're telling us that these solutions are aqueous. What does it mean to be aqueous? That means they're in water, okay? Now, usually there would be a kind of a little disclaimer on the side that says, assume that the solution is mostly made of water so that you can use the specific heat of water. Otherwise, we wouldn't be able to solve this problem, okay? So, now let's talk mass. Well, if you remember, 1 milliliter is 1 gram of water, okay? A milliliter is a gram. So, if I can switch, this is in liters, if I can switch each one of these to milliliters, which I could do pretty easily. So remember, if I'm going to a smaller unit, my number should be getting bigger. So I'm going to go 1, 2, 3 loops to the right, which makes this 50.0 milliliters. Well, that's the same thing as 50.0 grams because it's water, mostly water, okay? I know it's not exactly, but it's going to give us a nice approximation. Same thing here. I'm going to shift 1, 2, 3. That gives me 50.0 milliliters, again, which is grams of this solution, okay? So now all I need to do is figure out what my mass is. Well, what did I put into my calorimeter in total? I put in 50 grams and another 50 grams, which means I have a total of 100 grams. So this is equal to 100 grams total. Now, because I'm going to the tens place in both of these numbers, my addition should also go to the tens place. So it's 100 grams total of the water in the solution. I know the specific heat of water. Now the question is, do I want it in joules or kilojoules? Well, I can see here that it's in kilojoules or calories. I can see that I want it in kilojoules. So instead of using 4.184, I'm going to use 0.004184 so that it's in kilojoules per gram degrees Celsius. Okay. And now I need my temperature change. Well, it ends up saying that it increases by what, and again, we don't care about the sign right now. We only care about the sign when we calculate delta H. So it's 1.09 Kelvin. Well, then my Kelvin won't cancel out. What we talked about in class is the fact that the Kelvin and degrees Celsius change is the same. So what people will do is they'll make a mistake of saying, oh, well, I need to change it from Kelvin to Celsius, so I'm going to subtract 273. Don't do it, okay? The change is the same. So whether you change by 1 degree Celsius or you change by 1 Kelvin, that's exactly the same, okay? So now what I'm going to do is I'm just going to simply calculate this. And I get 0.456, so 0.3 sig figs is what I want. So 0.456. A lot of times you don't even use temperature for your sig figs. You use the rest of the numbers because sometimes they just give you an approximation, and it kind of makes it hard to be able to work out the problems. And so now I know that this is in kilojoules. Okay, not kilojoules per mole, which is what I wanted. So I'm not done yet, because delta H does not, if I cancel my units out, I am left with kilojoules. I can't just say per mole. It's for that reaction as it was run. So here's what I can do. If you remember from the last unit, if you have solutions and you want to calculate moles, what do? Well, if you remember, molarity times volume, N times V, gives you moles. So the question is, which one do I do this for? Well, I'm trying to figure it out really for the ammonium chloride, for this ammonium chloride right here. And what I can see is it's a 1:1:1 ratio, which means if I know the moles of HCl or I know the moles of NH3, I also know the moles of NH4Cl. It's exactly the same. So all I need to do is calculate one of them, and then that will tell me how many moles of the NH4Cl this is for. So all I'm going to do, and remember you do need to be in liters for this, so it's N times V will give me moles. So then I have my molarity is 0.200 molar. Multiply that by my volume, which is 0.0500 liters. And so then this tells me that my moles are 0.01, but 3 sig figs. So I've got 0.0100. Remember zeros to the left? Never count, but zeros to the right need a decimal in sight, so those are going to count for 3 sig figs. And so this is my moles. Again, that's moles of either one of them, okay? So just keep that in mind. Now all I need to do is get my kilojoules divided by my moles. So we're going to do this similar to when we did moles, liters, moles over liters, grams, moles, grams over moles. Now we're doing kilojoules, moles, kilojoules over moles. So all we have to do is once we know our kilojoules, once we know our moles, we simply divide to get kilojoules per mole. So divided by the 0.0100 mole. And just a quick tip on this too. So they tell you that you're not supposed to use a calculator on the AP exam. Okay, obviously a calculator is always the fastest thing to do. But I have a very easy trick, and I'll send a video out later. It's like a 5-minute deal, but it's pretty simple. The way that I end up doing this is I say, like, if it's numerator to numerator, you want them working in the opposite direction, and then you can figure out what your answer is. I always try to make it so that it's really easy for me to multiply or divide something. So for example, in this situation here, I know that 2 times 5 is 10. And so what I would do is I would write down the number 10. I shifted one loop over here and two loops over there. Now your answer, if it's numerator to answer, they need to go in the opposite direction because it's almost like multiplying and then dividing to get back so that they're equal to each other. If it's numerator to denominator, you want them going in the same direction, or denominator to answer. But if it's numerator to numerator answer, then you want to go in the opposite direction to cancel out. So I just did 3 loops to the right, which means I'm going to take this and I'm going to go 1, 2, 3 loops to the left. And when I do that, I get 0.010. But again, we want to throw in those extra zeros for sig figs, or that 1 extra 0 for significant figures. And so I get that same answer that's right there. Well, in this situation here, I know that 0.456 divided by 1, that's easy enough. So what I would do is, if I didn't have a calculator, I would say 0.456 divided by 1 is 0.456, okay? But since I moved my denominator 2 to the right, well, your denominator and your answer want to go in the same direction. So I'm also going to move this 2 to the right. So I'm going to go 1, 2 to the right, which means my final answer should be 45.6, and now it's in kilojoules per mole. Okay, there's one more thing that we need. We need the sign. Okay, we need to make sure that we remember to put the sign in. Because we said that the temperature was increasing for the reaction, I know that this should be negative, and so that is my final answer. So now I'm going to kind of switch gears for just a second here and let you know what happens and how a bomb calorimeter is different. What happens if you see a problem with the bomb calorimeter is they may not. It may just be exactly the same as a simple calorimeter problem, and they don't tell you anything different. But in this particular problem, it says that we have, same thing, we've got a 0.05 sample of 0.2 molar hydrochloric acid. It's also added to this ammonia. And then it says that it's put in a bomb calorimeter, and they're giving us the heat capacity of the bomb. Okay, and then I say that the temperature increase is 1.09 Kelvin. Calculate delta H in kilojoules per mole. Okay, so what I'm going to explain to you is this. If you use a bomb calorimeter and they give you the heat capacity, well, this is what's different about it. Mass is gone. In a bomb calorimeter, which we'll talk about later on, what happens is mass is constant. And since mass is constant, it's actually incorporated right into the heat capacity. So you notice it would normally be joules per gram degree Celsius or joules per gram Kelvin, but in this case, the mass part, the gram part, is gone. We don't need it. So if you want to know the energy in joules, for example, all we need to do is look at this. Oh, if I multiply these two, then my Kelvin cancels out and I'm left with joules. That's all I need. Okay, so why'd they give us all the other information? I'll show you why in just a second here. So all I'm going to do is 480 joules per Kelvin. I'm just simply going to multiply it by 1.09 Kelvin. And so my Kelvin cancels out. And what I'm getting is 523.2. Let's use 3 sig figs, so 523 joules, but I want kilojoules. It specifically says kilojoules. So I'm going to shift my decimal 1, 2, 3 loops back. So I get 0.523 kilojoules, but they want it per mole. So same thing as last time. All I need to do is take a look up here because it's still the 0.2 times 0.05. It's exactly the same problem as I did before. And so all I'm going to do is the 0.2 times the 0.0500 liters, and that's molarity. And remember, M times V gives me moles, so we had already figured out that this was 0.0100 moles. So all I'm going to do is divide by the 0.0100 moles. And again, don't worry about your sign until after. Same thing as what we were talking about before. So I know 0.523 divided by 1. So since I just moved, it would be 0.523. Since I just moved 2 loops over to the right, then I want to move 2 loops over to the right again. And so I'm going to get 52.3 kilojoules per mole. Again, the temperature increased, which means my sign is negative. All right, and last one on here, it says Again, I just want to remind you, even though it says bomb, sometimes it's in a bomb calorimeter, but the problem's exactly the same as doing it for a simple calorimeter. So you always have to check to see if they gave you the heat capacity of the bomb. If they didn't, then just assume that it was water inside of it. And again, we'll talk more about that in the next section. You and your lab partner add 100 mils of potassium hydroxide solution to 100 mils of sulfuric acid solution. Again, we've got a neutralization that's happening inside of our calorimeter. Write the balanced equation and then calculate delta H. Again, they want it in kilojoules per mole of the salt product. And it says the calorimeter temperature went up from 20 to 38 degrees Celsius. Okay, so it's going up. So I've got KOH, and I'm adding it to H2SO4. Remember, we get water and salt, so I'm going to get HOH, but my salt in this case is KSO4, which is K2SO4, because that's a +1 and that's a -2. And then I would balance my reaction, which means I have 2 there, and so then it means that I need 2 in front of my HOH, and so now I have a balanced reaction. They are telling me that the density for water is about 1, and we're assuming that, again, that it's aqueous. These are aqueous solutions. And then they also give us the specific heat of water, okay? All right, so all I'm going to do is work out my MCAT, and that's going to give me my kilojoule part of this. So delta H is equal to MC delta T. Everything needs to be for water here. So again, 100 mils is 100 grams. 100 mils is 100 grams if it's mostly water, which it is. So my total going into my calorimeter again is 200 grams. So you want to know what is total. And again, because they're mixing together, I can only do one solution, one MCAT. So now the specific heat, let's use the kilojoule value. So 0.004184 kilojoules per gram degree Celsius. And my temperature change, so from 20 to 38, which means it's 18 degrees Celsius. And we know that it increased. So all I'm going to do is multiply these 3 together, and I get 15.06. Again, it looks like 3 sig figs. Like I was mentioning earlier, we kind of want to leave the temperature out. Usually they'll give us more sig figs on the temperature anyway. So I'm going to say that this is 15.1. Okay, you really would have to just say 15 in that case, but 15.1, my grams cancel out, my Celsius cancels out, and I'm left with kilojoules. Once again, I know I wanted kilojoules per mole. Here's the situation. This is how it's going to be a little bit different from the one that we did before. It says of the salt product, which means I want this one. I want that product, not the water. I want the salt product. So the question is, if these two are different, which one do I use to calculate moles? Well, if you're thinking you want to use the one that has the same ratio that makes it easier, then that's true. Otherwise, you're going to have to do stoichiometry if you know moles of one and you have to figure out the moles of the other. But in this case, I would rather just do it for this, because then that is a 1-to-1 ratio. So that's a 1 and that's a 1. And then therefore, my moles would be equal to each other. So all I'm going to do is I'm going to multiply my molarity times my volume, but remember you have to be in liters, so I wanted to make sure you saw that again. So I'm doing M times V, which is 1.50 molar times 0.100 liters, because I want to shift my decimal 3 loops back. And so again, if I'm not using, if I'm using my tricks here, so because I want to do 1.5 times 1, then that would give me 1.5, right? So that would give me my 1.50 if I'm multiplying by 1. But since it's numerator to numerator answer, I want them going in the opposite direction. So in this case, I'm actually going to shift in the opposite direction. Since I went 1 to the right here, I want to go 1 to the left. And so my answer is 0.150 moles. Okay, and so now all I'm going to do is divide by 0.150 moles. And just so you know too, because it looks like it's about 15 divided by 15, and they would do that on the AP. They wouldn't do 15.1 divided by 1.5 by 0.15. So just to give you a little bit of an idea on that, and my final answer then is 100.66 repeating. And so I want 3 sig figs. So I would just say 101 and kilojoules per mole. Last thing, don't forget, we need a sign since it's delta H. My temperature went up again when I put it in, so that means that my sign is negative, and this is an exothermic reaction, okay? All right, we'll do a little bit more with calorimetry, but this is nice to at least get a start, and happy day, everyone.